What's that?
The delay for stream is just starts to look very intensive.
Could be worse. Okay, welcome back, everybody. That's loud. What's that? So last night's surveys told me that everybody likes it when I step up and try to mention the big picture and how things connect. So let me just start by leading in from what we did last time into what we're going to do today. Okay. Okay, welcome back, everybody. That's loud. So last time we talked a lot about LQR applied and how it was applied to a bunch of systems, right? So for the Acrobat, Cartpole, Ballbot, you name it. Pretty powerful tool. But it was a local tool, right? I tried to emphasize with a picture that, in particular in the phase portrait, we're coming to know well, right? The pendulum's phase portrait, that the linearization that we use for LQR was a very faithful representation of the dynamics in a small region, right? It actually got the dynamics, the vector field, really well in the region where the linearization is valid. All the arrows were pointing in the right way. It even did this, did all this good stuff. Okay, but it was inevitably the linearization is a good approximation over some domain. When x minus x star is small somehow. We'll try to quantify that more carefully later. Okay. And then given the linearization, LQR is was the optimal controller for the linearization. So that's a fairly indirect argument, right? To say that I'm going to build an optimal controller for the wrong system, right? And just hope that that description of the system I'm optimal for is close enough over some regime that it works. And it does work, and it works, I think in practice we'll see, and we'll be able to certify soon that there's some big swath of state space where that controller is, even when the nonlinear terms kick in, the controller is still going to be good. It'll still be stabilizing. The pendulum won't fall down. The Acrobat won't fall down, even though there's some nonlinear terms. It's not optimal for that, but it's sufficient for that. Okay? But the goal, in the value iteration story, we talked about trying to do value iteration for sort of all x, not just for some local approximation. So we'd like to try to talk about swinging up the pendulum and the like. We're trying to cover the rest of the state space today. And we had a proposal in value iteration for something that should work for that. And I want to think through how to do that, not just for the pendulum we've already done with a fine enough grid. But we're going to try to see how to do that, how much that can extend to bigger systems. If you're interested, and we'll cover it a bit later in lecture, but when I write it that way, I can't help but say that there's a better way to use linear optimal control if your goal is to try to, if you acknowledge that there are some nonlinear terms that you're missing, right? So you can use tools from robust control, for instance. You could say that this system is linear plus or minus some delta, and you can tell your linear optimal control about this uncertain delta, and you could get a controller that might have a bigger basin of attraction, right? So there are better ways from linear optimal control that could still address the nonlinear system. But this is the simplest path. Just pretend it's linear and build a controller that trusts that assumption. Okay, so how far can we get with value iteration? So we did it on a mesh, right, before, where we, you know, if you looked at the code that I did a demo of for the pendulum, I discretized the state space. You know, Q, Q was discretized into 51 different states, Q dot similarly in 51. So I got some mesh that was 51 by 51, you know, order 250 or 2,500 elements, right? Does anybody know why I picked 51? Seems totally bizarre, right? Why do I always have a 1 hanging off the end? Yeah.
So include the origin.
Right, you want to include the origin, right? So if I do, when I'm doing like NP linspace, I don't know if I did -2 to 4, what's that going to give me? That's going to give me like -2, you know, 2/3, -2/3, 2/3, 2. I don't want that. I always pick an odd number on the end. If I do -2, -2.5 here, then I'll get -2, -1, 0, -1, 2. So when I'm doing things from -pi to pi, I want to have an odd number so that I make sure I get a sample at the origin. I want to get 0, 0 solidly in my data set. Okay? Because we know that the cost to go goes to 0 at the 0 point. And if I'm going to talk about infinite horizon cost to go, if I don't have a place to get to 0 cost, then my infinite horizon cost is going to be unbounded. You need to let the system know how to get to some place where the cost stops accruing. So it's really important to have a 0 in there. So I always have like 31, 51, whatever I can tolerate. Okay, so that worked, and that's fine. That fits in nicely in memory, and we're all good. Okay, so for Acrobat, cart pole, you know, I'm in 4-dimensional space, right? So I get what, 51 to the 4th power? That starts to be a bigger number, okay? Still not, I mean, we could sort of deal with that. It's what, 6 million, something like this, right? But but it's worse than that. It's the fact that when we talked about the controllability, so the sensitivity of the dynamics to the controller means that the controller changes a lot. The gains are, you know, you need to have a lot of samples near the upright. That's effectively what kills you with the Acrobat, is that maybe 51's not enough, or you have to really cleverly place those 51 around the upright to do well. And in practice, even if you make this big mesh and you wait for a while value iteration tries to do its thing, you're going to get a controller out that still falls down. Okay, so you know, these numbers grow fast, so making a big mesh in harder problems becomes too much of an ask, and the more subtle problems need really fine discretizations. You know, quad rotors, if you wanted to do a full solution for quad rotors, you're going to do that in 12 degrees of freedom, 13 degrees of freedom, depending on how you parameterize your rotations. Those get big fast, right? You don't want to do 51 to the 13. That's too much. Okay, so we want to think about you know, ways to address that. And the natural way to address that, which we'll talk about today, is to think about how do you do value iteration not on a grid, not on a mesh, but on some function approximation, some function approximator. Right, so we're going to represent our estimate of the cost to go at some state x with a neural network I guess these days it's pretty much only a neural network. Yeah. I mean, there's other choices there, but people would even call them neural networks nowadays. And let's say with parameters, I want to denote the parameters explicitly. I'll call them alpha here. So, and I'll use a subscript alpha here to say I'm evaluating that function using parameters alpha. In the neural network, the parameters are going to be, I'm going to just call that a big vector that is all of my weights and biases. That define the parameters of the neural network, all in just one big vector. Just to make that super clear. So we've talked through what the value iteration update should be on a graph, or in the mesh we thought of as a graph. The question then is, how do I update the parameters of my network to do a value iteration type update? That's the first question, right? And what I want to update, of course, is the parameters of the network. Let's build that up. Okay, so in the fully discrete case, discrete and finite, where I had a finite list of states, and I could say that my j hat at si was just updated to be whatever I did from searching over all my a's of L of si a. Right, that was for the case of the loss, I'm trying to minimize the infinite horizon cost. This was my original update, right? So the goal, the question we want to answer is, what's the corresponding update if I'm using function approximation? Okay. Now, and you can think about how would I want to do this, right? So ideally, what I'd do is, as I've gone to continuous variables, what I'd love to say is something like, for all x, I'd like j hat of x to be something from the right-hand side, right? Min over a something. But I can't do that. I can't do it for all possible x. Right? I don't know how to work in the space of functions very well when the functions are this complex. Instead, what I'm going to do is I'm going to take a bunch of sample points x, okay, which I could think of it as being elements of some sampled version of the original space. I don't know if this notation is helpful without a lot of description, but I'm going to just pick a bunch of, let's say pick 5,000 or more. Maybe it's 6,000, 6 million or whatever, 6 samples in space. And at all those samples, I'd like to have something like this happening, but with my function approximation case, right? In this example, j hat was just a finite list of numbers. So I was able to just write a vector of, however many states I had one scalar number for each of those. I put it in a big vector, and I just updated the entire vector every time I made this update. Or I could make it a few elements at a time. That's a cool trick, but the point is there's a finite representation that was perfect for this. Here I have some finite number of parameters. I have the weights and biases of my network, okay, but I can only approximately say that the left-hand side, I can only approximately set the neural network's values to the right-hand side. I can only do it at a bunch of sample points, and even then, I can only do it up to some, whatever gradient descent can do for me, right? So once I have this, then this is the proposal, and we'll try to understand it thoroughly. The first thing I'm going to do is, at all of those sample points, I'm going to compute the desired, this is my notation for desired, the desired value here. It's a value iteration, so I'm going to have the desired based on my current estimate of my parameters alpha. And then, given the desired values that I would love my network to have, I'm going to write a small supervised learning kind of problem to do that. So I'll minimize a least squares error. I'll minimize over alpha the sum of those i's of the estimate at xi minus the desired value at xi. And we'll do it squared. Good old, this is a nonlinear least squares problem. That's sort of the natural correlate of setting it exactly at the values to trying to, this is like approximately setting it to the values by minimizing a squared error, which tries to make the estimate as close as possible to the desired. Ask questions about that if you have them, yeah? Some people are totally happy, some people are like, I'm not sure I know what he's talking about there. Okay, so I see that as a close analog to doing it, that first line, but doing it with a function approximation. Now, it's interesting, it's an interesting choice. So why did I call out this separate j desired as a first step and then write a loss function like this? That's a little bit different than what I could have done, and actually what I think most people's first instincts would be to do. This is not the same as if I just did directly minimize over alpha sum over I won't write everything here, but well, I guess I have to. But I just wrote the value of JD here, okay, but when I see this line, if I'm going to minimize alpha here, then I'm going to, there's alpha enters the equation in two different places. It enters in this value, this representation of J, and it also enters in this representation of J. So you'd take, let's say, a gradient of this and do gradient descent that would change the values on both sides of that. That is a reasonable thing to try for this sort of algorithm, but that's not what works in practice, what works best in practice, and what most of the theory is built around. The theory is built around this idea of first keep this alpha fixed, write it into a constant value here, and then minimize the objective. So it's basically freeze this alpha. Don't let this alpha change. Only change this alpha. Okay, some people, you'll hear this called like the target network approach. you'll see in PyTorch or whatever, you'll see people just make a copy, they'll call it a target network, and they'll use the target network on the right-hand side. Before that, I mean, people talked about 2 timescale algorithms. There's names for that idea, but certainly it makes the analysis simpler, okay? And in fact, there's both a substantial practical justification and even some theoretical justification for why people do this. They will only take the gradient on this side. Okay, but given that one weirdness, hopefully that's a reasonable thing to just say. I want my j alphas to be approximately this, and then I'll run through the crank of supervised learning here. Once I have that objective, I can minimize that objective the nonlinear least squares using your favorite gradient descent. You can use atom, whatever. We tend to use atom for when J is a neural network on these problems. That's the one I've had the most success with. I think your mileage will vary, but we'll use mostly atom in the examples I give you. You can also do all the standard supervised learning tricks, right? So it would be quite common to make a lot of samples here. Try to put a lot of samples that cover in some random or systemized way the entire space, and then do a mini batch update. So each time I make an update to this, I'll just take some random subset of those samples and do mini batch. I think those are the most important supervised learning approaches that we'll use here. Okay, if you're not, you'll see that I don't think I need to make a formal statement of what mini batch is. If you're not familiar, it's easy to read in the code. Okay, that's the proposal. Big question, but does it work, right? How well does it work? When does it work? When does it not work? Are there anything that we can learn from our superpowers of understanding closed form solutions in relatively small problems that would help us understand, what's going to happen in the harder problems? Maybe we can look carefully at what this does in some simple cases and learn some lessons that will carry on to some bigger problems. Okay, so there are some theorems that can get us started. I should say in the fully general case, the answer is no guarantees. But in practice, we can do, there are some limited cases where there are guarantees, and there's a lot of success in practice. Okay, so let's think about the very important special case. Linear function approximators. This is the one that you'll see. I think as you'll see, it kind of separates out the nonlinear least square, the challenges of nonlinear least squares from the challenges of just what happens with approximation in a value iteration loop, right? We can turn this into a linear least squares problem on one side when the function approximator is a linear function approximator. So what is a linear function approximator? It sounds super limiting, but it's actually not. It's actually a very rich class. I mean, it's not as rich as a deep network, but if I were to take my function that I want to approximate and just represent it as the linear combination, so it's linear in the parameters, but of potentially nonlinear features. If you prefer, you could think of this as just, if I write out the sum, I've got a bunch of nonlinear features of my state space, and I'll just sum them up here to make my estimate. So it has to be linear in the parameters, which is limiting, but the fact that this can be arbitrary function of x means that this can be it's a pretty rich class, actually, of function approximators. So you'll see people using radial basis functions. Actually, the barycentric interpolation that I was doing behind the scenes in the mesh code is actually, you could think of that as formally as a linear function approximator. Interpolation. I mean, a support vector machine, this is a support vector machine idea, right? This can be the kernel trick where you can have lots of different functions of x that make this, if you know support vector machines, right? That's sort of the same richness, is that even linear functions in a kernel space can be really rich, okay? Support vector machine, for those of you that know that. Now, an interesting one, which you could say sort of maybe the ultra-wide neural network case, right, is people are talking about. Are kind of like this. So there's the neural tangent kernel, which I've mentioned once or twice before, but some people argue in the theory of ML that the way to think about a super huge neural network, especially in the limit where the second to last layer is ultra wide, is actually as a bunch of, a huge network behind the scenes, which is making effectively, random features like this, and then a linear network at the end, and that's why overparameterization. That's one reason why overparameterization can get you to zero training error. So, but there's maybe some limit where neural networks could be thought of this way, but I got to say this is not what's happening in practice. In, let's say, RL for robots. I think we're far from this regime. Okay, so what can we say about linear function approximation, right? So the key idea, which I just said in words, but let me write out here, is if I want to now do the minimization over alpha at some sample points of now, even though my j desired is an arbitrary set of numbers here, that could be the result of the Hamilton-Jacobi evaluated on the other side, and my features can be nonlinear, this equation in the value iteration update is a linear function of alpha. So this is now linear least squares. And I can solve this. I don't need gradient descent. I can just solve this in closed form. That's got a closed form solution. So you see there's multiple things happening, right? Even though I made a call out to supervised learning when I wrote this, analyzing the performance of these algorithms is more complicated than supervised learning because it's like supervised learning with a moving target. Every time I change alpha and I come back here, my desired values are changing, right? So I've got two dynamics here. I've got the dynamics of my desired thing moving and I've got my dynamics of trying to converge on this nonlinear loss. Those things have to get along for your algorithm to do well. And if we can just take this second one and say, I don't have to worry about doing a few steps of gradient descent, I'm going to just solve this one to global optimality. Then we can remove that part of the dynamics and just focus on the alpha, how alpha goes through. And so that's why the linear function approximators are such an important special case for analyzing these. Sorry, Alex. The linear function approximation, the convergence results and the like for linear function approximation started in the fully discrete case, which you might think is funny because it's really the continuous states that motivate function approximation in my mind. But maybe even if you have enough discrete states, you can try to compress those. And certainly, it's a cleaner problem. So people, in my notation, were thinking about representing that big vector. I already had a big vector, but it's just a really big vector. And I want to approximate that basically with a smaller vector. So this might map, my 51 to the 4th power down to a vector of like, the interesting regime is where this is maps some really high dimensional vector down into some smaller space by having alpha b size 1,000, let's say. The classic result here was by John Tsitsiklis, who's in the department, and Van Roy. And Van Roy. It's a 97 paper. It's linked from the notes. And they proved that under some assumptions, in the linear function approximator case, that algorithm that I said, this fitted value iteration, that's what we're calling the value iteration where you have to fit the parameters of a function approximator, showed that in this setting, we have strong convergence results. That alpha goes to alpha star. I haven't even defined what alpha star is, but alpha star makes it, j hat alpha si as close as possible. It minimizes the error between the j star si. There are rules, there are conditions inside there you have to do. If you're going to do gradient descent, you have to do it well, and there are some regularity assumptions and the like on some of these things, but like you have to be able to, I think ergodicity or things like this are properties of the discrete graph that are required for this. Okay, but for our purposes, this is a big time result that says actually even though I'm using function approximator, I can enjoy some of the same guarantees that I'd get in the in the discrete case. They say with probability 1. We'll explore that in a few minutes, right? So if you randomly draw your initial alpha, then with probability 1, you'll converge to the optimal solution. There are newer extensions to understanding this in the continuous setting, but they have to make certain assumptions, and not all of those assumptions, as we'll see, are guaranteed for robots for the kind of problems we have. You have to look when you read a theorem saying, guaranteed to converge, continuous setting, neural network, for instance, you should look at the assumptions carefully because the full problem is still hard. All right, so let's try that. Let's try to understand that in even the LQR setting where we have closed form solutions and the like. If I did value iteration on LQR, am I guaranteed to converge to the optimal LQR? Right, we solved it with a closed form solution, but if this works, I should be able to get that out of my algorithm too. And the cool thing is that if I say j hat, and let me call the parameters s in this case, is x transpose sx, you'll see that immediately as a quadratic equation in x. But for the purposes of now, you should see that as an equation that is linear in s. Right? You could see that any different way, but it's linear in the coefficients s. So this is a linear function approximator. I could write that in the form of s parameters transpose, xx transpose stuff. So I can expect, I would like to expect the Sitsiklis and Van Roy problem to carry over and say, this is going to work for me. Okay? So I'm going to basically, let me actually show you in the code. Here's LQR via fitted value iteration. It's hidden at the bottom of the Lqr chapter. Coded up recently. It might have not been there the last time you looked. Okay. In the Lqr problems, I can solve for the optimal s. Okay. So I'm going to do that at the beginning always, and then I'm going to check whether the convergence goes to, whether it converges in the optimal s. My function approximator, my cost to go function here, is just linear in s. So the only decision variables are s. Is that big enough for people to see? Should I make it bigger? You probably having trouble. Yeah. All right. Don't need that to be bigger. Yeah? OK. So I'm going to do my, I happen to do this in 2 steps, but I basically make my j desired is the min, I don't need documentation, is the min over, good Lord, let's put it over here, OK, is my g, which is just my pre-computed 1-step cost, plus j next. I have to do some game, in NumPy you have to do some games to vectorize everything so that it's fast, right? But this is just the vectorized version of summing over all of those x's, okay? And then I take a min over u with some reshaping and taking a min over the right dimension. That makes it less readable, and I don't like that, but it's, I promise it's just what we wrote on the board here. And then I compute the j desired minus the approximation, and I compute that loss and the gradient of the loss as just my Bellman residual. And then I'm just going to do a step of gradient descent. Actually, I'll do 10 steps of gradient descent for every time I go through that loop. And the question is, I mean, we're leaning on the shoulders of giants here. That should converge, right? That should work. I should be able to converge to the optimal cost. I have eigenvalues of s printed out and the optimal s printed out. So I'll go ahead and this is my loss as it's running along. And you want that to go to 0. Not going to 0. OK? Yeah, I zoomed so much that I can't see my stop button. OK. So what went wrong there? I guarantee, and so this, there's the math is right. The code is right, I think. Like I can make it work. We're going to make it work in a second with a simple change. But let's just think about what just happened. What's the disconnect between the trying to write the LQR like this and what we've talked about so far. What are some ideas about what could have made that go wrong? If I do value iteration on S, that's for the double integrator, by the way. What could possibly have broken that? You have ideas? I should check if I had an odd number of everything. Okay, yep, I did have the origin in my data set. If you miss the origin, it's going to blow up, right? But I had the origin. I don't have a discount factor in here yet. We're going to see what happens with a discount factor in a second, but that's a good idea.
Can you check that your S guess is positive definite?
Good. It turns out that so that's a great question, actually. My S guess is the identity matrix, which I can assert with no further math that that's positive definite. And diagonal, which is, or sorry, and it is diagonal, but it's also symmetric. This goes back to some of the questions you guys were asking on the value iteration, the first time we talked about the value iteration, and how do I interpolate from one state to the other. So one thing I've done here is I've sampled x and u. So I made a bunch of u's from -1 to 1. It includes the origin. But what goes wrong here is that from those x's, that u may not be the one that gets me exactly to the origin. Right, so I've got if you think about the discrete graph, I had a bunch of points here. I've got a bunch of sample points, no shortage of sample points. I've got 9 possible u's coming out of each one of those. But none of them got me exactly to the origin. And that's bad, because you have to get exactly to the origin to obtain 0 cost. Okay? If you don't have a place in your value function where you're getting to 0 cost, then the infinite horizon cost to go is infinite. And every step I run that algorithm, it's just going to say your cost should be bigger and bigger and bigger and bigger. So actually, the gradient descent is doing great, but it's tracking a target that's saying I expect infinite cost over time, because I don't get to 0, and any small number rolled out into summed over a long time is going to get big. Okay. So how do we fix it? Yes?
When you mini-batch, do you also need to have that 0 point in every single batch?
It's a good question.
Have it in some of the batches?
Yeah. I think our remedies, so the question was, if you mini-batch, do you have to have that 0 in there? I think you better have it often, is my guess, yes. Or you do one of the other mitigations that that we talk about. So you said discounting, right? So what about discounting? So very common in reinforcement learning, instead of minimizing the long-term running cost, I'll try to minimize over my actions some discounted loss. Where gamma is between, I guess probably you want it to be strictly greater than 0. When gamma is 1, then you've just got the original infinite horizon cost function that we've been solving. But when gamma is smaller than 1, this is going to help convergence, right? So even if L has non-zero values over time, it's going to be squished by decaying exponential function. So that can have a finite, that can converge to a finite value even if L does not converge. Yeah? And we see this all over the place in reinforcement learning. And as I gave away by having gamma here in my options here, we can fix this. Well, first let me also say, this is a problem you can study in the closed form solutions too. In fact, you can solve for the discounted infinite horizon LQR problem. It has a Riccati equation just like the original one. You can find the closed form solution given gamma. It's illustrative, I think, to see what happens. So normally, this is the discrete algebraic Riccati equation. The discrete one looks a little different than the continuous one. It's ugly. It's so, like, considering it should do roughly the same thing in the limit, it's ugly. So I'm just going to write DARE, discrete algebraic Riccati equation, instead of writing out the whole Riccati equation. Okay. So if I had the undiscounted one that was a function of A, B, Q, and R, and I add discounting, then what happens? It actually is, you get the almost, you can use the same algebraic Riccati equation. It's as if you had passed in a slightly different A matrix and a slightly different R matrix. That's a cute thing to, it's easy to verify if you go through the discrete time LQR derivation. But the reason I want to highlight it here, I mean, that's first of all what I did in the code in order to solve for the optimal discounted function. But it's also interesting because you can see that the effect of putting that gamma on there, it's like I'm taking my dynamics and pretending that they're more stable than they are. So if this is a small number, and I'm worried about in discrete time having the eigenvalues of A be greater than 1, this is making the eigenvalues of A closer to 0. So it's kind of, discounting is kind of like pretending that the world is simpler than it is, right? In precisely that way. It's an equivalent derivation. Okay, so that way using that, I can put the gamma into this and adjust both the closed form solution that I'm comparing against and the numerical solution. And I'll have a quite different experience now. The loss decays quite nicely. I did it conservatively just to make sure the demo worked, but you probably I could have turned up the learning rate a bit and really, or just gotten a faster computer, honestly. At home, it's like this, but. Sorry, I should optimize on the lecture machine, not on my fast computer at home. Okay, it converged at 570. It didn't have to go all the way. The eigenvalues of the estimated S were this, and the optimal S, sorry, the estimated S was right there. I put the eigenvalues in just to make sure that I got the positive definite S, okay, just to say those are both positive. And the optimal S is numerically very close. Actually, it's a little farther off than I expected. I wonder if I screwed something up. Huh. I think I removed my gamma somewhere. Well, I will fix that tonight. But that should match exactly, and does in all my previous experiments. Okay, so that's cool. Gradient descent, fitted value iteration works for LQR if I have a discount factor. It's interesting, you can kind of mess with the discount factor. You can, like, 0.92 works, 0.93 gets pretty dicey for this problem, just with that level of discretization. That's very unsatisfying for me, because I don't want to have to, like, pretend the world is different than it is. I don't want to have to discount. There's a closed form solution to this. Why can my value iteration not find this easily known solution, right? This feels like, if you have to discount to get a good solution, something feels inadequate. And in particular, this you should realize that you can find a controller that's even optimal for a discounted problem that would be unstable on the system you're trying to control. Right? This is really pretending that the world is more stable than it is. You could find an optimal controller with finite cost on a discounted problem, and then you put it on the real robot and it goes poof, and blows up. Right? So discounting is useful. It's a nice way to be more sloppy with the loss functions. You don't have to be as careful that this goes to 0, but it has some penalties too. Okay, here's a different, I think, better solution that gets rid of having to put a discount factor in. Remember in continuous time LQR, I made a big deal when we talked about the continuous time Hamilton-Jacobi equation that one of the great things is we could solve for U analytically. We don't have to discretely sample over U and search. And if I'm blaming here that I don't have the right U in my data set to get me exactly to 0, then I could do the same trick here. For LQR, it turns out I can solve for U whether it's discrete or continuous. That one's simple enough that I can do that. Okay, so don't sample U, use the LQR controller. Specifically, right, so in LQR, we said, for instance, that U equals negative k of x. There's some optimal k, okay? And we even broke it out. We know that it's negative R inverse B transpose S star of x. That's in continuous time. There's a similar thing in discrete time. It's just more ugly. Yeah, I even wrote it here in case I thought it, but it's just too many. It's like 17 symbols for the same thing, okay? But it's simple. It's just too many symbols, okay? So what I'm going to say here is the proposal is that I'm going to put in U equals negative kx, where I'm going to have this be the estimated one, right? Given whatever my current value function estimate is, I'll take the thing that's trying to go downhill as fast as possible, subject to my actuation abilities and subject to my preferences over cost. I'll take that as my controller. Whatever my current guess is of my cost to go, I'll go down that as fast as possible, and I'll use this for my U and replace the sample-based U. I've done that here. You see I solved the algebraic Riccati equation with the square root of gamma times A, R divided by gamma, exactly what I said. The only thing I'm going to do different in this notebook is I'm going to use the LQR policy for U, given my current estimate of S. The LQR policy is just, there it is. That's the discrete time one, right? It's like, it's not as nice. Okay, I'll do the same thing for 0.9. Converges quickly. Even faster at home. And see if I got it right here. See, look, that time I got it right. So 0.86, 0.44, I mean, to many decimal places, that one's converged, right? Optimal solution. But hopefully this will convince you that it really was the action discretization that was causing problems. If I do the same thing again with gamma equals 1 here, that will also converge beautifully to the optimal solution. Okay? The only difference between this notebook and the other one was whether I did a min over u by sampling, or if I took the min over u using that. And now I don't have any discounting required. It'd be pretty funny if I looked away and it blew up. It's going to converge, I promise. Look at that. It's a different, see, that's the other thing, right? It's a different controller. The gamma gives you a different controller when you have that in there. But this one converges to the right values which are different than the discounted case. OK, that's converging from a particular initial guess. But can I say something about, is it going to converge for all guesses? I guess I converged from S guess equals I, right? But there's another subtlety here, even in the linear function approximation case, that we can understand completely with LQR. I'll start on a new board. The Riccati equation in continuous time was this, remember this Q minus S, there's no transpose, B R inverse B transpose SX plus S A transpose, or SA plus A transpose S. And remember, this was a quadratic equation in S. This was the thing that defined the optimal cost to go for the linear quadratic regulator. And we said the optimal solution is the unique positive definite solution. So there's exactly one solution of this where S is positive definite and symmetric. But there are other solutions, okay? There are negative definite solutions of S. Right? So to convince you, the simplest example I can come up with to convince you, let's just do Q dot equals U. Loss is just Q squared plus U squared. That means this is equivalent to having A equals 0, B equals 1, Q equals 1, R equals 1. Right, so those terms disappear. These are basically, this gives me a new Riccati equation, which is 1 minus S squared. Okay, that's like the simplest LQR problem I could possibly do. And there are two solutions, right? And LQR, when we solve it, takes the positive solution. But we haven't, we've told the Riccati equation solver to do that. We haven't told value iteration to do that yet. It seems like an important thing that we left out, right? And it can get into problems, okay? So let's just think about it. Since this is so simple, it's a flow on a line. If I plot over Q, I'll plot two things here, right? I'll plot my cost to go function. This would be J star of Q, which is S squared. But there's another, oh, sorry, this is just Sx squared. I wrote it like that. There's another solution. I don't know why I picked red for the good one and blue for the bad one, but my bad. This is negative S Q squared. So my cost to go function is upside down. All the stuff we talked about, when I'm here, my flow is such that the gradient of my cost is at the rate of my, the gradient of my cost to go is at the rate of my cost. That's still true, it's just going in the wrong direction. The partial differential equation is satisfied everywhere. The Bellman error is 0, but you've got an unstable controller, right? This one, the red one, gives you a nice, the optimal controller is just negative Sx, so I get u equals negative q, which is a nice stable controller. That other one, though, gives me this unstable controller. It's just going to blow up. But it satisfies the partial differential equation everywhere. Okay? So there is an important difference between the tabular case, where you have finite mesh, you have finite number of possible states. Because the thing that goes wrong here is I haven't told it anything about the boundary conditions. I haven't told it it's bad to run off to a negative infinity. Okay? On a mesh, on a discrete graph, you can't run off to negative infinity. Right? And it's tempting to say as the limit of that goes to very many cells, but still there's something about the boundary conditions that's missing from just the value iteration update. And that's real. You can converge, value iteration can converge beautifully to an unstable solution. Okay, so just to prove that, I took the unstable Riccati solution for, actually, even though I'm solving the discrete time here, I just use the continuous time Lqr as the unstable solution as a guess, and I start it from there, and that one doesn't go so well, right? Okay, so it's a linear function of approximator, but it doesn't actually converge. It converges super well. In fact, I think in this particular problem, we can say, and I tried to say it in the notes, that the unstable solutions to the Riccati equation are fixed points of the value iteration update, but they're unstable fixed points. And the positive solutions are stable fixed points of the value iteration update. So that's pretty good. Like most of the time, you'll converge nicely to the upward one. But if you start near the other one, I guess you could, this will probably eventually converge to the top one, but it's doing really bad things before it gets there. Like big numbers, it's not going well. Any questions on that? Did that point land? So, okay, in practice, what does this mean when you're using value iteration on acrobats and quadrotors and humanoids? I'm not sure if we can do humanoids. But so a lot of times, people will say, we'll try to start a lot of theorems, for instance, in control and sort of learning for control and the like. They'll assume that you have an initial controller that is stabilizing. So instead of starting from like arbitrary S in this case, you'd start from some situation where you know the controller is at least stabilizing. Things aren't going to blow up. And then if you proceed from there, you're normally in a good place. But the guarantees are subtle, right? Even though we have this acyclous result, the guarantees in continuous spaces are still subtle. Okay, on to bigger problems. I was just checking with our known solution here. That was the linear function approximation case. Let's think about the neural fitted value iteration. So now this is going to be a neural net. Now it's interesting, people talk about deep RL, right? And there is deep RL. I mean, I think like AlphaGo and the like is, I would say, using deep networks to do RL. But actually, I was faced with a choice at the beginning of class. Either figure out how to get you guys GPU access on deep note, or so in practice, basically in control, people use pretty small neural networks. And I was like, screw it, I'll just write some fast C++ code, and then we won't use PyTorch right now. So we have relatively small, a few layers, multi-layer perceptrons, multi-layer perceptron as our standard network of choice for this. Yeah, so I actually yanked PyTorch from the class repository, and I just wrote some multi-layer perceptron code directly in Drake, just so I didn't have to. I mean, at some point, if your networks are small, even the cost of going from our C++ code in Drake over to PyTorch and back is like exceeds the benefits of having a GPU optimized neural network when your neural network is a few layers and a few things. So this runs pretty fast. It's maybe not on that laptop, but this runs pretty fast and should do the job for all of our control problems. Okay. So the linear function approximator case, the LQR case, we had these good solutions and these tricks. Okay. Remember that in the discrete time setting, if I now have a linear or a nonlinear function approximator, a neural network here, taking this min over u, if I just argued that it was a good idea to try to take that min over u smartly, not by sampling. You could sample and just take the smallest one here, but that can run into problems. Okay, so how do I take the min over u now? Even if my cost function is convex in u, I have to get that through the neural network. And this side is definitely not convex in u. Right? So solving that min over u looks harder in neural value iteration. In practice, a lot of people will use actor critic, if you know, for instance, to get around this problem. But we shouldn't need to do that here, I think. And because of the trick I've told you about before, if I use instead in continuous time, this was discrete time. Now I'll do continuous time. If I want to take the min over u with respect to my loss plus partial j, partial x, f of x I u. Okay. If this is convex in u, and we said this is going to be control affine in u often, then the question is, even if I've got a neural network here, is that okay? Can I solve for that u in closed form? And I can, right? So even though I've got a huge neural network sitting here, all I'm taking is the derivative of the neural network, and I'm multiplying it by my dynamics. So even though I've got a neural network in the way for my function approximator, I can still solve for the min over u in closed form. Okay. This I can get from autodiff, from backprop, the backprop algorithm. And then what I'll do is, what I'm going to recommend, I guess, for the fitted value iteration algorithm is to actually use this continuous time limit to solve for the minimum u. There's a fully continuous update you could do for the parameters alpha. You could just think about that you could think about making sort of alpha dot You could have a rate of update of alpha that would be consistent with the, all the differential equations. But I think it's fine if you've taken U, and you could just then use the discrete time J desired. So J desired xi is going to be the L xi plus my U star solved from that times dt plus J of J hat alpha of x plus f of x. Star dt. This is just sort of the, I think it's going to look to you, it should look to you as like a little bit of a mix between the CT and DT, but this is what I use to derive the DT. And in practice, you're going to make, somewhere you're going to make a discrete time approximation of the continuous differential equation. I'm just advocating that it's simplest to do it here, because then it fits right back into our supervised learning setting. I can do minimize over alpha, sum over xi. Same thing we did before. So that's a way to take, I think, maybe the best of the learnings that we've seen so far, but do it at on a function approximator that's got a lot more representational power than the examples we've used so far. Again, I always like to check, like it should do the right thing on the double integrator, it should do the right thing on the pendulum, and then I have some faith it's going to do the right thing on the Acrobat and stuff like that. Okay, so let's just make sure it does. Here's my double integrator neural fitted value iteration. I forgot to, let's see. Okay, I actually, even for myself, just to make sure I was happy with my architecture choices, since I have the closed form solution, I did a step where I went through and just said, okay, given the neural network, and just if I know the optimal solution, how well can the neural network represent the optimal solution, right? Just I tuned my architecture that way. You could see that, I won't run that, but I did that for the minimum time cost and the quadratic regulator cost, and that's sort of a luxury that I don't have in most problems, but I did it here. And now I'll do the fitted value iteration exactly like we just saw. That's the known optimal solution, and the red is the known optimal solution, and the blue is the value iteration converging very rapidly to it until it does converge. That was the discrete time, continuous state discrete action case, where I did a min over u, and I had some discounting. So that was the case, the first case we studied in the other one, where you did take a min over u, and it had a little bit of artifacts at the edge because of that min over u. It converged because I have discounting in here. And then I can do the fully continuous time, state, and actions, the fitted value iteration, and that one does even better. Well, all right, that just nails the optimal solution. I mean, up to some tolerance beautifully with a really small network. For these, I was just, I mean, two layers, two hidden layers, and like 32, 16 or something like that, rectified linear units. So 2 inputs, that's the 2 states, Q and Q dot, 16, 16, and 1. I did ReLU, and identity on the end. So that's kind of pretty good. Okay. I think since we're out of time, I'm going to delay talking at full detail about these, but we're going to let you run these for bigger systems on your next PSET, actually. But this is going to go more of the distance, not to the really big problems, but it's going to work pretty well I think, for the small problems. There's a lot of like implementation details. I was reminded of them by deciding to type them all into C++ instead of using PyTorch. I had to like remember all the different things that were important, right? Some of you will know this, but it's useful to just write it down, right? So the weight initialization really matters. Whatever you pick for your default alpha, your default weights, right? PyTorch picks one, most people don't even think about it, but if you get that wrong, things go badly, right? Atom really helps. I was just doing gradient descent, and I wasn't very happy. I was tuning too much, and if I switched to Atom, which is a different optimizer, similar to gradient descent, but it's got momentum, it's got scaling, that really made a big difference. And then I think the mini batch really does help in big problems, especially for big problems. I guess there's one other one to mention is for pendulums and acrobats that could possibly go around a full 2 pi, you'd like your network to be, by design, periodic in 2 pi, right? So if you put in q and 2 pi q, you get the same answer, right? So typically, the way I've done it here is I actually have a feature layer at the beginning that where I would, instead of passing in, whereas before I might have passed in x and y directly into the neural network and got out j. The standard thing would be to, if x wraps around, I'll take x and y and make the features sine of x, cosine of x, y, and then pass those into the first stage of the neural network. And that gives you something that's by default periodic in 2 pi, and then you can backprop through that to get your great partial j partial x is still with respect to this x. Okay, and it gives you good cost to go functions and the like. So we'll play with that some more on your P set, and maybe I'll, if I have time next time, I'll show a little bit more too. Good. So we have our continuous time fitted value iteration that should, and we understand hopefully a little bit more about it. See you, not Tuesday. Tuesday's a Monday, right?